Okay, welcome back in Power Electronics. This is module number 4, week number 13. We'll talk about another applications for power electronic converters, and then we move to protection of our converters. So I will talk about using power electronics converters in DC drive, AC drives, and then we go for protection from electrical and thermal, let me say, problems. Um, Let me start with DC drive. Before I start with DC drive, I would like to mention that in general, any movement require a motor, and motors could be classified mainly into DC and AC, and AC three-phase, single phase, and single phase are different type. Three-phase also we have induction motor, we have synchronous motor, and so on. So while I'm talking about the converters, I need to revise what you already studied in the previous semesters regarding the DC machine, the DC and then AC machine. Now, first of all, we will talk about DC drive. DC drive is used in many applications, and as you know, we have series and shunt and separately excited DC motors. Okay, and if you look here, just to remind you, I will do revision first about DC machine. You have armature here and you have field. For the field we will use rectifier circuit, controlled one, and for the inverter, for the field also we will control using rectifier. We study rectifier, different circuits for rectifier circuits, we already studied them, and here we are going to control the operation of the thyristor to control the voltage applied to the armature or to the field. Also, another, let me say, method is by using rectifier but diode one uncontrolled, and then we put DC-DC converter, buck boost, Cook converter, any one of them. Now for DC motor, let me start with separately excited DC motor. As you can see here, we have the armature circuit here, we have the field circuit here, we have inductance and resistance on the field, inductance and resistance and back EMF on the armature, and shaft connected between the motor, the armature, and the load. Also, we have angular speed and delivered torque, while here we have the load torque, moment of inertia and viscosity. Now, as you can see here, the voltage across the field, the voltage here applied across the inductance, which is LDI over dt plus Ri, as you can see here. And the same thing, the voltage applied across the armature is the voltage across the inductance, which is LDI over dt plus IR across the resistance and the back EMF, as you can see here. While the back EMF is function of speed and field current, while torque delivered from the motor is a function of the field current and armature current. Okay, here are constants. And the torque delivered equal to the JdW over dt plus BW plus TL. Okay, you already said this, but just remind you. And if we talking about, this is the previous one is instantaneous. If we're talking about steady state, then V field apply only across the resistance, because the inductance, I mean, the drop is 0 there. And the voltage across the back EMF voltage is omega IF, as you can see here. And the voltage across the armature is drop across resistance plus back EMF, which is already can be substituted here to become in this way. Delivered torque also equal IFIA by constant, DD is BWTL, and power delivered is T delivered times omega. Now from here, from this equation, we can find the omega, the speed, with respect to the other parameters, which is VA minus RAIA over V field I field, or V I field is V field over R field. Now from this equation, we can conclude the following. We can control the speed here by controlling the voltage VA, or we can control the current IF of the field current, or we can control armature current, keeping I field constant, fixed, okay, because the problem of saturation. Okay, so controlling any one of them, VA, I field, IA, sorry, all of them will give control on the speed. So how we can control the speed? But by the way, when control speed, we control the torque. How we control this? We control it using power electronic converters. The characteristics of the separately excited DC motor can be classified into two parts: constant torque mode, let me say, and constant power mode. In constant torque mode, it's clear that the torque will be constant, but the power increase. Okay, and the field current is the same here as the same thing for the current of the armature. While in constant power mode, we will find that the torque will be reduced sharply while the power is fixed. The same current all the time is fixed, but the field current will be reduced now. Problem of saturation needed to be considered here. Okay. Now another motor is the series induction, series DC motor. Series DC motor, the field and the armature are connected in series. So we have inductance resistance for the armature and for the field and the back EMF. Okay. Here we can see that the constant torque here is constant with the constant current. Okay, the armature current is the same field current because they are in series, and the power increase. This is for constant torque. But for constant power, okay, torque will reduce and armature current also will reduce. Here are list of the equation for series motor. You can see the difference here is we have resistance armature with field in series, so we add them together. Okay, and again, if we go through these formula, we will find formula representing the speed, how we can control the speed. Again, voltage, IA, IF, okay? But here, because of the IF is the same, we can't say it's only armature current and voltage can be controlled. Now, when we control them, we use them to control, use the power electron converters to control the voltage or the current. What type of modes we will have for the motor? Motor will work in 4 modes, different modes. Okay, in terms of voltage, in terms of voltage and current, or in terms of torque and speed. Sometimes all of them, torque and speed, are positive. Some of them, sometimes one of them is positive, either the torque or the speed. Sometimes both of the, negative, and some of time all of them negative. These are in 4 modes. The first mode is the normal mode. Power coming from the supply to the armature here and the field. This is for separately excited. For series, it's coming from the supply to the armature. It's normal motor. Regenerative braking, what happens is we return back the current from the armature to the supply. So the motor here work as a generator, generate back. You may say, why we use this for braking? You know, to brake motor, okay, braking have applications. I mean, in industry, we need movement and we need stop in some places. So braking need to be done. Braking either electrical or mechanical. Mechanical, we have friction. We have many problems here, there. Okay, and it's not that smooth that electrical. Electrical is more soft, smooth, flexible, and so very accurate to control. So for that, they use regenerative braking. Motor was working as a motor, provide mechanical energy, and suddenly it's start providing electricity, so returning back the energy to the supply, as you can see here. This is called the regenerative braking. The same thing happened, but just here we change the direction of the field, then it will change the power production and returning back to the supply, as you can see here. How we change the direction, I will explain it later in the next few slides. Another one is dynamic braking. It's similar to generative braking, but rather than we return back to the supply, we change by the supply by resistance, and this resistance can be variable resistance. We can control the consumption or the energy return back here to make it fast or slow braking. Okay, plugging, we will change the direction of the armature. Okay, current is changed its direction, but the voltage of the armature also to be changed here. How we changed it, I will explain it. Okay, you see here the 4 modes. I put them here on the X and Y, torque and speed. You can see here all positive, here speed, torque positive, negative, here both of them, torque and speed negative, here in this quadrant number 4, all of them, speed negative and torque positive. Now, after this introduction revision for the DC motor, let's go for our power electron converters, how we use them to control the motors. As I mentioned, we either control voltage, armature voltage, or field current, or armature current, and this need to be done by a controlled rectifier. We discussed control rectifier, remember? Okay, different type. We have half a bridge, full bridge, half control, full control, and so on. Single phase, three phase. Okay. Now, how it look like the circuit in the box? You get it from the market as a box in different sizes according to your motor. Okay. Now you may ask, okay, how we change the direction of the field current or the armature direction? It's very simple. You can see here we put a switch this way. This is switch. Okay. So if we connect here, the current will come flow here in this direction, back here. So if we connect here now, the current will follow here in the opposite direction exactly. Okay, the same thing could be say for the field. So we can't change the armature or the field current direction. Also, we may use here as example full control. By the way, this is a freewheeling diode for protection, as I mentioned, and this is half wave control rectifier, and this is the freewheeling diode. So if I use this, we have formula. We discussed this formula in rectifier circuits, half bridge. And for full bridge, we have, you can see if I use here full bridge, I can use the voltage for full bridge, as you can see. So how it look like in the markets, look like this. Circuits, we just need to control it and then control the voltage, control the speed, torque relationship. Now for AC drive, we have induction motor and synchronous motor. As you know, we have limited time here, so I would like to focus on induction motor, which is because it's the main motor used in this industry. But before that, I would like to revise with you the principles of the induction motor and their formula. You remember that the speed is synchronous speed is 2 times omega angular speed over pole number of poles, and the voltage is sine as we usually assume it, and the flux is flux maximum cosine omega mt. Omega m is the rotating speed, delta is the angle, phase shift angle, and then omega s is the speed, synchronous speed. If we derive it, this phi, with respect to time, rate of change, by and multiply by n, we got the voltage according to Faraday and Maxwell. So when we derive it, we have here this formula, and since we defined the slip of the motor to be synchronous speed minus omega m over omega s, then s omega s equal omega s minus omega m. Okay, so we can let me say we can convert these into s omega s, and we ended with this formula. Now this formula can be represented in the equation in the circuit of the induction motor. As you can see here, this is the rotor circuit. The rotor circuit will contain resistance and x multiplied by synchronous speed, because it's function of speed, which is function of frequency, and the same thing for the voltage, which is function of synchronous. So if I divide everything here over s, okay, then we have here x, and as you can see here, and so we can see that if we put them together, stator and rotor, we have here the x and r for the stator and x and r for the rotor. These are the voltages and the turn ratio. And if we put them in equivalent circuit, we just need to add here in between stator and rotor the core elements, which is x and r in parallel. And by the way, the current is representing voltage over the total impedance, okay, of the circuit. Now, if we go for power and torque, we can find that there is some losses in the stator, which is called PSU. It means stator copper losses, which is 3I square R, because 3 phase of the stator. And there is also rotor copper losses, which 3I square, but I R dash, which is transferred to primary, RS. And there is P copper core losses in the core, inside the core of the motor, which is 3 Vm square over Rm, as you can see here. Now the energy is similar to transformer. Energy transfer from one winding to another winding. So we have P generation. P generated is 3IR square times R of the rotor transfer to primary over S, which is function also of synchronous speed. And the power delivered is the power generation minus rotor losses, copper losses. We know we have the both formula. If we substitute and simplify, we'll have B generation 1 minus S. For the delivered torque, it is equal to power delivered over omega m. And omega m, as you know from the definition of slip, is omega s 1 minus s. And the power generation here is power derivatives, power generation 1 minus S. So if we cancel these, we have power generation over omega S. Now if we go to the input power and output power is 3 VI cosine theta from the principal, which is the core losses, copper losses are the primary, and generated power. While power output is the delivered minus the no load, which is the losses at the end. So if we substitute them and consider that P generation is higher than these losses and P delivered is higher than P no load, then we can simplify it to be in this way. Okay, cancel PG with G. What is left? 1 minus. Oh, this tells me that the efficiency, which is output over input, is 1 minus S. Yes, this is what we come up with. Now, definitely for the electrical elements, the total impedance we have at the end, primary in parallel with core losses, in series with the secondary. But if we go to the approximate circuit where the core loss is shifted to the supply, then primary and secondary are in series in parallel with the core losses. Their impedance and their phase shift is represented by this one. It's easy to find from the equivalent circuit, and the current also represented ID by VS as IR by VS over the total impedance, or here we ignore the core losses, or let me say core elements R and X, or also the torque delivered is 3 RIS square over S omega times the impedance of the circuit. Now, if I take torque delivered here and try to see what parameters I can use here to, or let me say change here to change the torque, and then if I change the torque, I change the speed at the end. Okay, we can see that we can control by changing VS, which is stator voltage control. Okay, or changing the rotor control because I have R. So if I have the rotor to be changed, the voltage will be changed. And also we change the slip or omega S. Let me say we have frequency, so we can control by controlling the frequency, or we can control stator voltage and frequency, or we can control stator current because resistance is there. Okay, and we can control all about control voltage, current, and frequency together. So it seems to be that induction motor can be controlled. We have wide range of parameters to be controlled here to control the motor. Then comparing with DC motor. Now let's take the first one as example. If I want to control the voltage, stator voltage control example, this is example. You can see that the voltage here, if I multiply it by a ratio P, which is B, from 0 to 1, okay, in this way, VA is BVS, okay, then which is equal to KMW phi. Then phi can be rewrite this formula. It will be B